Good afternoon. I am Vishwajit M. Gaikwad from Department of Physics, Amolakchand Mahavidyalaya, Yavatmal, Maharashtra. Today I am going to present my recent research findings on effect of Fe substitution on structural and magnetic properties of DyMn2O5. So this is the outline of my presentation. I will discuss introduction, statement of problem and objective of my work, preparation of Fe substituted DyMn2O5 samples, results and discussion section including structural, morphological and magnetic properties, and lastly conclusion and acknowledgement. So basically multiferroics are the materials which possesses more than primary ferroic order parameters. Multiferroic materials are in demand because of their potential applications in magnetic field sensors, spin filters, magnetoelectric and spintronics, and for data storage application. Basically, multiferroics are classified into two categories: type 1 and type 2 type of multiferroic. But type 1 type of multiferroics, the magnetoelectric coupling is very weak, and there are two different elemental sources for ferroelectricity in magnetism. While in type 2 type of multiferroics, ferroelectricity exists itself in the magnetic order state, and they show strong coupling between electric and magnetic parameters. Among type 2 type of multiferroics, Rmn2O5 family of compounds is important because of their significant electric and magnetic properties, and they show the strong interaction between 3 degrees of freedom, that is spin, charge and lattice. So among Rmn2O5, DyMn2O5, that is DMO, is capable of showing magnetically induced ferroelectricity, large magnetodielectric effect, large magnetoelectric coefficient and significant electric polarization. As per the structure of DMO is concerned, DMO crystallizes into orthorhombic structure with PBAM space group. The orthorhombic unit cell of DMO consists of two Mn sites. Mn4 plus sits at the octahedral sites, while Mn3 plus sits at the square pyramidal sites, and these octahedra and square pyramids are interconnected by corner sharing oxygen. The magnetic structure of DMO consists of two blocks, that is block A and block B. In block A, Mn4O6 octahedra is connected to two pyramidal units, while in block B, Mn4 plus O6 octahedra is connected to two Dy3 plus spins. But due to symmetric exchange restriction, these two Mn3 plus ions shifts up in block A, and here two Dy3 plus shifts down in block B. So due to that shifting, the polarization, that is PMM and PDM, is generated in the block A and block B. So this is nothing but the magnetically induced ferroelectricity or magnetically induced polarization in DMO structure. So thus the tuning of the material properties through atomic substitution is very important in the field of experimental condensed matter physics, and DMO compound illustrates the strong 3D 4F coupling, and bulk DMO possesses antiferromagnetic ordering at Néel temperature 42 Kelvin due to Mn ordering, and at 8 Kelvin due to Dy3 plus ordering. And the magnetic structure of DMO can be tuned by replacing Mn3 plus and Mn4 plus by Fe3 plus. Thus it motivates us to design Fe substituted DyMn2O5 samples and explore their structural and magnetic properties. So we have opted co-precipitation route to synthesize Fe substituted DyMn2O5 samples using aqueous ammonia, and this is the flow chart of the methodology. So structural conformation of prepared sample was carried out by X-ray powder diffraction, and raw XRD patterns are analyzed by Rittville refinement technique, and all the samples crystallizes into orthorhombic structure with space group PBAM, and the structural stability of this compound was observed up to Fe concentration is equal to 0.5, and afterwards the strong strong secondary phase of FeO3 was observed. So therefore we have restricted our studies up to Fe is equal to 0.5 concentration. So when we see the magnified plot of 1-to-1 reflection peak, so this 1-to-1 reflection peak is shifted towards lower Bragg angle with Fe substitution. So this is the clear indication of lattice and unit cell expansion. Lattice and unit cell expansion. So the lattice parameter C and volume V increases with increase in Fe concentration, and we can see the rapid escalation of cell volume and lattice parameter C is observed after concentration of Fe concentration of 0.2. So this is because of the reduction of Jahn-Taylor distortion of Mn3 plus ions due to Fe substitution. So the unit cell of DMO and Fe substituted samples are constructed by using VESTA program. So these are the unit cells of DMO and Fe substituted samples. So it consists of Mn4 plus O6 octahedra and Mn3 plus O5 pyramidal units, and they are both interconnected by corner sharing oxygen, and the magnetic exchange lengths are extracted from these unit cells, and we have found the magnetic exchange lengths for Fe substituted samples are lower than that of DMO. It means that the strong magnetic interaction is observed for Fe substituted samples. So these are the structural parameters, and we can see that the cell volume increases with the Fe concentration as well as Fe concentration, and the magnetic exchange lengths are found to be reduced or are found to be decreased with increase in Fe concentration in Fe substituted DMO samples. So this is the Fourier transform infrared spectra recorded at room temperature in mid IR range from 400 to 800 cm inverse. The vibrational vibrational modes were observed in the range 450 to 550 cm inverse. They are related to MNO bonding vibration in pyramidal unit. The strong transmission mode or strong vibrational mode observed at 640 cm inverse. These modes can be correlated to MNO stretching vibration in MnO6 octahedra. New mode that is related to FeO bending vibrations was started appearing for the sample Fe is equal to 0.3 DMO samples. So this is the clear indication, or this is the signature of the introduction of Fe3 plus ions at Mn3 plus site. The DMO sample shows spindle type of particle shape with average particle size of 200 to 300 nanometer. When we substitute Fe into DMO lattice, the morphology get transformed from spindle to particles or to plate or sheet-like structure, and the particle size get reduced with the Fe substitution. So the defect induced by the dopants can be pushed from bulk lattice to the surfaces, and as the number of Fe3 plus ion increase, the large number of Fe3 plus ions are expected to go to the surface sites of DMO. Hence it prevents the aggregation of the particles, hence the particle size reduces with Fe substitution. So these are the EDAX or EDS spectra of DMO and Fe substituted samples. So it shows the expected chemical composition of elements. So the temperature dependent magnetization, that is MH curves are recorded at 5 Kelvin temperature, and all the samples shows the non-saturated hysteresis slim curves, which is the indication of weak ferromagnetic character, and the hysteresis loop do not get saturated because for Fe substituted sample, weak ferromagnetic interaction cannot prevail over AFM interaction, hence the loop do not get saturated. So to estimate the exact saturation values, we have employed law of approach to the saturation model to the initial magnetization curves of DMO and Fe substituted DMO samples, and the MS values are extracted by LAS fit. So these are the plots are showing the magnetic parameter dependence of Fe concentration. So we can see that the magnetic parameters, that is MR, remnant magnetization, coercivity and saturation magnetization, are decreased with increase in Fe concentration up to the concentration up to 0.2, and afterwards these magnetic parameters got enhanced. So after Fe is equal to 0.2 concentration, the magnetic strength get increased, and this can also be correlated with the structural parameter, where we have seen the increase in cell volume and cell volume and lattice parameters see rapidly after the concentration of Fe is equal to 0.2. The temperature dependent magnetization studies were carried out at 100 oersted film, 100 oersted field under the field cooled and zero field conditions. So the ZFC FC curves of DMO sample shows typical antiferromagnetic nature, which shows the antiferromagnetic transition temperature 42 Kelvin is due to the Mn ordering, and at 8 Kelvin is due to the dy3 plus ordering. But as Fe substitution increases, as Fe concentration increases in DMO lattice, this transition temperature got shifted towards the higher temperature from 42 Kelvin to 68 Kelvin. And the nature of ZFC and FC curves for Fe substituted sample shows the existence of ferromagnetic order along with the AFM ordering due to the strong magnetic interaction of these chains Mn4 plus O Fe3 plus O Mn4 plus magnetic interaction. So in conclusion, we can conclude that orthomagnetite, that is Fe substituted DyMn2O5 samples, were successfully prepared and stabilized by co-precipitation route. Structural studies indicate slight increase in cell volume and reduction in exchange length of magnetic interaction. The average particle size of sample decreased with the incorporation of Fe3 plus into DMO lattice. The reduction in exchange length between Mn pins increases the strength of magnetic interaction, leading to enhanced magnetic parameters for higher concentration of Fe. And empty studies show the Fe substituted sample indicated appearance of ferromagnetic order along with the AFM, with shift in the transition temperature towards higher temperature. And these studies may develop an intent to further exploration of magnetic application of RMn2O5 types of multiferroids. Thank you very much.